So I've made a program that can turn whatever messages you have, or any binary data really, and turn it into what it would look like when it's in DNA-based pairs. This is all done in Python, and it's pretty simple. I'll walk you through it right now. To start off, I define what the dictionaries are, so how I'm translating this binary stuff into DNA-based pairs, and vice versa. Then I have to define these variables because they're in the functions later on, and that's how Python works as far as I know. There's probably a better way, but I'm not a Python expert. Then you can choose what type of thing you want to translate. So is it toDNA or from DNA? And then it can call one of these two functions. The first function is toDNA, so basically it would turn whatever string you have and turn it into binary, and then it will turn the binary into bits of 2 because that's how we use the dictionary above, and then it will iterate through that, turn it into DNA, and then you just join all the DNA together into one string, and it will return that. And from DNA is kind of the same thing, except it will make a list from 1. So it'd be, you input your DNA sequence, input the text, and then it goes through that, uses the binary list again, and turns it back to binary, and then there's an additional step to turn it back into characters. And then this is just the if-else clause of how, we get to the decisions made. If the input text was to DNA, then it will ask, what is the message you want to translate, call the function, and then you get the outputs. And then the second part is from, and if you choose an option that isn't available to any of those, you'll get not a valid option. Now, the way you'd upgrade this, have something here that allows you to scan through the entire DNA string you give it, and see if it has A, C, T, G, and only those letters, and not other letters like Z. Second way is to allow this to actually take image data. So, because everything is stored in binary, there's a way to take it out of it. So while the coding part is pretty simple, when you actually want to translate this into the real world, it's quite difficult. Data stored in this DNA wouldn't actually work in your body because your body doesn't read binary, it reads genes, it reads, sequences of DNA that are put in a specific way that code for a certain thing. And that code is not the same as binary by any means. But as we learn more about the human genome, and as we learn more about amino acids and how DNA turns stuff into what we are, because there's a lot of ethical concerns when it comes to DNA, because DNA makes up our body. So if you were to put it in, a cell that multiplies, which is a stem cell, or maybe the cell where you're born from, then you could produce something that could be horrific, that could be a different human, that could be, similar to the AI apocalypse we know today. If, for example, we wanted to create a DNA sample of everything in the human body, and we wanted to grow that, right, then that would be equivalent to making an AI robot that could, that is completely different, that is completely engineered by us. Now, that's cool, obviously, but there's obviously a lot of ethical concerns around that because of the potential it has to, destroy the world. And also, it just feels weird because, you're choosing what a person does, looks like, and everything about them, potentially their entire future, and that just goes against human principles of accepting people. Now, that's what DNA data storage shouldn't and can't do, but why is DNA data storage more efficient? Well, we already know what hard drives and SSDs look like. They are physical quantities that look, a decent amount of size. But DNA is molecular. It's quite literally very small. And because of that, it is very, very dense. And since we can store 2 binary values inside DNA, makes it a lot more efficient. But DNA being molecular, right? If you were to, compact it as much as possible, you could store all of the world's data in just a kilogram of DNA. And for reference, an adult human has almost 2.5 kilograms of DNA. So all of the world's data for that much mass is pretty good. Now, synthesizing this DNA is actually very hard. First off, that would be a lot of DNA. Second off, synthesizing DNA for data storage is very different. So first, let's go over how normal DNA replication works. So there are some pretty good videos about this, but DNA, essentially, this is going to be the DNA backbone, and let's say these are nucleotides. There's going to be a protein that comes in, which we'll make with this rainbow pen, and we're essentially going to make it go over the whole thing. And what it can do is it'll start from, let's say here, it'll press a primer. And then it'll continue to copy DNA, so forth. Continue to copy DNA, but it's only able to do this because there is an original copy. So now, here's another way to look at this. So you're going to start with your original strand of DNA, and basically, that's one DNA. And then it has to copy. So it'll go to these two things. It'll differentiate, it'll break apart these bonds, it'll break through the middle, essentially. You'd have your original from there and your original from this side. Now what will happen is once the protein comes along, it will start copying, and it will make these 2 copies. but it only does that because it's a parent strand. Now, if we were to replicate, new DNA, that's called de novo DNA. That's harder to make because none of it is something we already have. We don't have the parent strand. So you'd literally be starting from one, and you'd be adding one by one. And first off, that's very slow because you're not just copying, pasting, first off. And second off, it's something we haven't done before. If you're gonna do that, then it's gonna be hard. And it's also difficult because most methods of, making this DNA involves either a strong base or a strong acid. Now, that strong base or strong acid is likely to wear and tear the DNA as it starts from the beginning, because imagine this: you have your DNA, put the next one on, then soak it all in acid, add the next one on, soak it all in acid. By the time you have 100, right? By the time you have 100 DNA base pairs, you have this DNA pair exposed to acid 100 times. And the next one's 99 times, and so on and so forth. And you have potentially damaged DNA. There's some research around this, and there's a company that has found a way to use enzymes instead. Now, enzymes are usually made of proteins, and they, in the body, make everything work better and faster. In this case, we're able to put the DNA strands one by one with just the enzyme, and there is no change to the DNA because you're just adding it with an enzyme. Imagine it as like puzzle pieces being put together. So that's the main thing. There's obviously the other side, which is reading the DNA or sequencing it. So sequencing is actually pretty cheap because we've actually done it for so long. The Human Genome Project started a while ago, and it completed, quite a while ago as well, probably over a decade. Since we've sequenced DNA for so long, it's actually easy for us to do. Now, on that note, the reason we're looking into DNA storage for another cause is because we have to store data for a long time. This DNA's data storage has the potential to last longer than current data storage methods. Cheaper, maybe not, but longer for sure. There's two methods, which is freeze-drying the DNA, which would eventually, make it last for millions of years because it's freeze-dried, nothing can change it. It'd be have to put in like a freezer chamber. And the second way is in vitro storage, or basically just storage in aqueous solution. So it'd be stored in a solution with different compounds that protect it from UV rays and other elements. Now, the reason for that is because DNA is pretty fragile. As you guys know, skin cancer exists. That happens because UV rays hit your skin. Now, the same thing can happen if it's in literally just a vial of water. More UV rays can hit that than it hits our skin. So that's why we need to store it in a chemical that can protect it from UV rays. That has shown to last, a little bit less time, probably 100 or so years. But as we find better compounds, we're able to make it last longer. And the reason we're making it last longer is because imagine humanity falls. And humanity dies, falls, humans are alive, but there's no technology, and everyone's ooga booga. As a technological civilization, all humans will always have DNA. So if they find our vial of DNA and happen to keep it, or just it's stored, then they'll eventually find a way to sequence DNA again. And binary is something less likely to happen again, because maybe they'll find a way to compute with base 10, which is like, letters 1 to 10 instead of 0 and 1. And also, we might be able to store the DNA inside a living body. So this is where the injecting DNA into your body gets a little bit weird, but that involves research because a lot of DNA, they start with start codon for genes. I forgot the exact one. I think it's ATG. And once it starts from there, it'll keep going along the strand until it finds a stop codon. That's going to be the gene. But if we find a way to mark our DNA in a different way that doesn't interfere with the current DNA process and current process in the body, we can store this inside a human, which makes it, quite a bit better, because then we have storage for generation and, potential generational data storage that only happens within one person. You can save grandma's recipe only along your bloodline, which is kind of funny. Now, all in all, this is a cool field, but is it very practical? Not yet. That's why there's more research around it. That's what I was looking into and have talked to people about. Will I be continuing to explore this topic? Maybe a little bit. I will probably look into DNA synthesis, but what I'm looking into next is going to be something a little bit more complicated, but something a little bit more practical. So I hope you enjoyed learning about DNA data storage, and stay tuned for the next video, because the next video will probably come out. Now, I know this content isn't what I typically make, but I'll continue to make content like this, but I'll also go back to the self-improvement motivational ones that you guys always see. But yeah, I'll be there. So until then, peace.